So once we have finished applying all the loads and boundary conditions, now what we need to do is we need to solve this particular problem. So I'm going to click on here to solve this particular problem, on the solve button to solve the particular problem. What happens, it is going to create the global stiffness matrix, global displacement matrix, global force matrix, depend on the boundary conditions, geometry, material properties and everything, and it is going to solve all the equations, and then it is going to find out the deflections at each node, and once it finds out the deflections at each node, it is going to interpolate that particular values using something known as the shape functions, and then it is going to represent the deformation, it is going to represent the stress, it is going to represent the strain throughout the total body. Now see, once I have solved this particular problem, now what I am going to do is I am going to select the solution group from the outline. So once I select the solution group from the outline, I can ask for different sorts of results. So for this particular problem, I am going to ask for a total deformation, and I am also going to ask for a directional deformation. And then the next step is we need to find out the equivalent stresses or von Mises stresses. So for that purpose, I am going to go to the stresses group. In the stresses group, I am going to select the equivalent von Mises stresses. And remember, depending on the type of analysis you are doing, because Ansys mechanical can support lots of types of analysis, like say model analysis, advanced dynamic analysis, transient analysis, fatigue analysis, lots of other nonlinear analysis. So depending on the type of analysis, whatever the results you are going to find out will be varying. So here you are only performing linear static structural analysis, so you will be getting only some type of results. But if you are going to change the type of analysis to dynamic analysis, there the number of solution options that are available will be changing. So once I have done all these things, I am going to just right click on the solution group once again, say evaluate all results. So what happens is, evaluating all results means whatever the results that have been created and that can be only understood by the computer will be converted into the results which we have requested here. Okay, now if I click on this total deformation in the outline tree, see, I am able to have or I am able to see the value of deflection inside this particular cantilever beam, which is displayed on the graphics window. See here in the graphics window, you can see the result we are seeing or we are watching is the total deflection, and the units it is being represented is in mm. And see here, I have got a maximum deflection of 0.75063, and this particular maximum deflection is at the free end. As we already know, at the fixed end the deflection will be 0, and at the free end the deflection will be the maximum. So this is the total deformation. But coming to directional deformation, so instead of selecting the total deformation, you can even see what is the deformation in each direction. It may be x direction, it may be y direction, or it may be z direction. So in this particular problem, we have applied the pressure in the downwards or negative y direction. See here, negative y direction. So what I need to do is, I need to change the axis of calculation from x-axis to y-axis. So what happens, see here, by default in the definitions tab, you are going to have the orientation set to x-axis. So whenever you put up directional deformation, the orientation by default will be x-axis. But here in this problem, I want to see the deflection in the y-axis direction. So what I am going to do is, I am going to change this orientation from x-axis to y-axis, x-axis to y-axis. Once I select this x-axis to y-axis orientation, I need to once again update this particular result. For that, what I am going to do is, I am going to right click on that particular result, and I am going to request for evaluate all results once again. So once I have done this, see here, we have got the deflection, and this deflection is in the y direction. This deflection is in y direction. So what happens if we take this particular end, it is 0. So it is a fixed end. At the free end, we are going to get a maximum deflection of 0.748 mm. So it is represented in a negative value because whatever the deflection we have calculated, it is in the negative y direction. That is why it is representing that deflection as negative. And coming to the contours, so in the total deflection, see, the highest deflection was represented by red, but here what happens is Here also the highest amount of deflection according to the software is 0, because if we take negatives, 0 is the highest number. So that is why it is representing the highest value here and the lowest value in blue color here. So as an CA engineer, you should not go away with seeing different colors, and you should not be say telling based on the colors, you should not be saying whether the component has failed or not. You should be able to understand these particular results, and you should be able to interpret these particular results. So coming to the final one, which is nothing but the equivalent stresses, you can see the maximum amount of stress has occurred at this particular constrained end. So what happens is, when we apply the force, in addition to the stresses that are induced inside the body, there will be some reaction forces that are caused due to fixing of this particular end, and these two add up and we get the maximum amount of stress here at the constrained end inside a cantilever beam. So this is how you can request for results, and you can perform linear static analysis on maybe a cantilever beam, or it may be some other simply supported beam. If you are going to calculate simply supported beam, what we are going to do is, instead of fixing this end, we are going to select this edge and that particular edge, and we are going to fix two different displacements only. We are not going to fix any third displacement, and we are going to apply the pressure here on the top, and we are going to find out the results. Now if you want to understand even more, if you want to understand these results even more, you can just press on this animation button. So there is a graphics section here in the Ansys mechanical window, where you can just press on this play button, so that it is going to play, and you will be able to see an animation of the stresses being developed inside this particular cantilever beam due to the applied pressure. So in the next section, or the next problem which we are going to deal is, we are going to take a pneumatic cylinder cover, and then we are going to apply pressure on it, and we are going to perform a linear static structural analysis on a pneumatic pressure cylinder cover. Thank you.